So the work I'm going to present has been done in collaboration with Mike Ortiz from Caltech, JP Mendez, who was former student in Sevilla, then he did a postdoc at Caltech, and now he's in Los Alamos. And Francisco Arca, also a former student, PhD student, and Javier Ramos, also working in Sevilla. So I'm going to start kind of telling you a little bit about what we have done in this field, in graphene, and then our recent results that are the part of the title of the talk. So as a way of motivation, so graphene, a 2D material, it can be fabricated by different means, but when you, for real materials, what happens is that they all have defects, mechanical defects. And the important properties in graphene are the electronic, thermal, chemical. You all know all these very promising properties, but they all are sensitive to lattice imperfections, defects. I forgot to mention, I'm a mechanical engineer by training and also by heart, so you will see it. Everything is defects related. So graphene turned out to be a key material for the next generation of electronic devices. So once we identify defects, what we are going to do at the end is to see which of them are more interesting, what kind of defects are interesting for these kind of electronic applications. So in order to end up at this point, you need to identify what defects are going to change the electronic properties. Point defects, for instance, can change these electronic properties, and also linear defects, as you see here. Linear defects, you can think of grain boundaries. Also, if you add some elements, doping elements, you are going to change the electronic properties, but we are not working on that, because for that you will need some special interatomic potentials, and you have to rely on the quality of those interatomic potentials. So it's something that we haven't done so far. In order to study the electronic properties, you need time-binding potentials. This is the second day, so this has been mentioned already in the room. So of course, since the applications are electronic devices, temperature will always be there. So you have to be careful, and once you identify defects, study their thermal stability. So this is also part of the studies that we conduct in the group. So electronic properties, it's well known that graphene doesn't have band gaps. Graphene, I mean, perfect lattice. So when you have a special geometries, like nanoribbons with some edges defined on the given direction, you will see some band gaps. So this is something that is well known also. And when you have grain boundaries, of course, some grain boundaries, you are also going to observe band gaps. So what kind of grain boundaries? They have to be symmetric grain boundaries, because symmetric grain boundaries, they don't open any band gap. So let me talk a little bit about our approach. How do we face this kind of analysis? So we are able to study properties of individual defects. When I say individual defects, are core structures of dislocation, core energies, okay, this kind of stuff. For that, we use our harmonic approach. I mean, we did develop that approach in 2005, and the first paper on graphene was in 2010, so years ago. Since then, we have been working and developing some other, applications. So this harmonic approach is based on discrete lattice elasticity, discrete dislocations, and as eigendeformations. This is the way we introduce slips within the lattice, and we introduce dislocations in a very easy way. And we study, as I said, we study properties of individual defects and the stability of those defects. In order to study the stability, because we are starting with a harmonic model, you have to relax the configuration. Relax the configuration means that you have to take into account the nonlinear effects. So how do you account for those nonlinear effects, the part of the energy that you are not accounting for at your first step? So we can either use our anharmonic approach based also on the harmonic approach that I have already mentioned, or you just use your configuration with the defects already introduced, and you relax the configuration using a well-known molecular dynamics code, or I will rather say molecular statics, because we try to avoid the kinetic energy, reducing the temperature in order to focus on the potential energy and the stability of the defects and structures that we are going to be working with. So our harmonic energy looks like this. So this is the term. This B operator is where you have all the interatomic potential information. Those are bond-wise force constants that you can obtain from different interatomic potentials. And here what you have is the bond deformation minus the eigendeformation. So this is the elastic deformation. Very simple equation, an equation that is going to allow us to really get defects in a very easy way. And the good thing is that those defects are stable, and you can identify them very easily. So these are the kind of slips that we introduce, slips along a zigzag chain of bonds, and we obtain this eigendeformation in terms of individual discrete slips in different interatomic bonds, as you see here. So then we minimize this energy, and we obtain the configuration that corresponds to that kind of slip introduced within the lattice. Of course, because we are accounting here at this point only for the harmonic part of the potential, you have some out of equilibrium forces within the lattice, and this is accounting for the nonlinear effect. And if you follow an iterative procedure, you will end up finding the very relaxed configuration. Okay, very, very simple. I don't want to spend more time explaining this part of the work. So, as I said, the harmonic deformed lattice, then we follow the relaxation procedure in 2 steps. In this one, we use, at this point, we use the periodic boundary conditions for the MVT molecular dynamic relaxation, but it's important to then, after this step, continue with this another one, with the conjugate gradient, in which the boundary conditions are flexible, because you are going to have out of plane displacements that are going to relax the lattice, are going to reduce the energy, and if you keep the periodic conditions, the lattice are going to be undergoing some strain, compression or traction that are going to change the energy. So it's very important to really follow this step and end up having the very relaxed configuration. So I have already mentioned interatomic potentials, And so we started with a harmonic model by Ariza and co-authors. This is the first interatomic potential we work with. Then we have been linearizing bond order potentials, the very well-known Ariza potential, or this another potential accounting for large deformations. We linearize them, we obtain the force constants, and we see how they compare with in between them and with other works. You can, also time-binding potentials. You can linearize them, although we are going to use them in order to compute the electronic properties, but some people say, okay, you cannot, you shouldn't do the mechanical part using a potential and then study the electronic part using another kind of potential. No problem. We just linearize the time-binding potential and we end up having the same kind of structure of defects that we have with the Ariza potential or any other potential. So you always have to be careful and compare everything and be sure that then you are accounting for all possible problems, let's say, that you can have. So if you compare the force constants that you have, this is because you have to compare the whole set. So it's a bit, doesn't make more sense. So we do compare the phonon dispersion curves, and the comparison is fair enough with empirical values, different kind of potentials. If we compare both bond order potentials that we have been linearizing and compare with empirical values, okay, the comparison is fair enough. So we...
you actually compute an interatomic from the type binding models.
The force constants model from the tie binding potential, yeah.
Are they good?
Yes, yes. They are here.
But it's kind of an indirect way to get an interatomic potential, right?
No, we get the harmonic part of the interatomic potential, which is the one we need in order to use our harmonic energy. That is in a very simple form, and it's going to give you the structure of the core of the defects, and from there you just relax the configuration. So it's an easy way to get well-defined defects, and then use the second part, the nonlinear part of whatever interatomic potential that you're going to have. But it's two steps, but each of them are more simple than the whole thing done at the first, in one step. At least this is my opinion. So, okay, the stability of, the true thing is that the stability of those core structures we have checked then. And you see here, for instance, the quadrupole configuration. So this harmonic approach is capable of predicting stable cores, stable core structures, and they are thermally stable too. We have checked that. Okay, so let me talk about linear defects, grain boundaries in graphene. So this is the supercell that we define. I'm not going to talk about symmetric grain boundaries, only asymmetric grain boundaries, because I want to talk about electronic properties. So this is the way you set up your computational cell. You have a grain B, grain A. So with this configuration, with different misorientation angles, A and B, we define this cell, supercell, and then we relax the cell for a given number of angles. So those are the configurations, the stable configurations of symmetric grain boundaries that we have found. We have computed the energies and compared the energies with previous results. The comparison is good. I mean, following the steps I described before, relaxation using the MVT plus the conjugate gradient relaxation. So these are the configurations that we have obtained. You see that you see an array of these 5-7 rings that usually appear in graphene when you have topological defects, combinations of these 5-7 rings. So different periodicities for different angles. We have even found for the same angle 3 different configuration of defects. I mean, this has been observed also by other authors, so it's not anything weird. And you have to look at the out-of-plane displacements. So you are going to have local wrinkle structures along the 5-7 rings, but very local out-of-plane displacements in some cases. But in other cases, in addition to the local wrinkles that you are going to have along the grain boundaries, you observe this secondary wrinkle structure. It doesn't appear in every configuration, but in some of them. In other cases, what you observe is these out-of-plane displacements. So they are quite different, in appearance at first sight, but we will see in a moment the effect that these out-of-plane displacements have on the electronic properties. If you plot the energies of all these different grain boundaries, what you get is a picture like this one. I mean, comparing with other authors. So it doesn't really tell you much, just looking at the energies of those grain boundaries configurations. So you have to look at something else. So if we study the transport properties across grain boundaries with this Landauer-Whittaker formalism, in which you have to define here the grain, and then you need to account for this. These have to be left and right. You need to have perfect lattice, so you have to be careful to define the size of your supercell in such a way that here the lattice is perfect, here is perfect also, in such a way that you can have this configuration. I mean, something that is already well described. You know what you have to do is only taking you to larger or smaller supercells, depending on the periodicity you have to account for different grain boundaries. Nothing really complicated. So this is an example of what I was saying. And if you compare the transport gaps that you obtain, you see that these differences. For different grain boundary configurations, you see that some of them they open a band gap and some of them they don't. And the gap that they open are different. You see all these values. And what you observe is that, remember the pictures that I showed before, only the energies were not telling you much, because the gap that you are going to obtain depend directly on the mismatch value, the lattice mismatch that you have within the lattice. What is this mismatch? You have two grains, different angles. This value for both grains is not exactly the same. This mismatch is the difference between these two values, meaning that one grain is going to suffer some deformation, in-plane deformation, and that little deformation that they are going in order to adjust the grain boundaries, the borders, and so that deformation that the lattice has to, the different grains have to they suffer are the ones responsible for opening a band gap. So deformation within the lattice is going to give you band gaps, otherwise you don't get those values that you really need in order to use graphene for electronic devices. So what are the values that we have observed? So we have first compare in this case, are there differences in between in order to, once you compute the electronic properties, to use the lattice with the 3D, let's say the 3D definition, or just the flat configuration that you can, once you compute this real size, the right size of the supercell after relaxation, do you have to use the 3D model, or can you just use, in order to compute the electronic properties, the 2D model? It's just a question of having, larger or smaller calculations. So the first comparison that we did was, to obtain these curves for both cases, flat cell or the 3D fully relaxed cell. And what we observed is that the band gaps were the same. So here you see differences here in the curves in both ones, but those are not important, because what is really important here is to know this part of the curve. So this really telling you that in order to obtain the size of the cell, you have to account for the out-of-plane displacements. But once you already know the dimension, the geometry of that supercell, you can forget about the out-of-plane displacements once you come to compute the electronic properties. Again, it's something that you have to really check how important it is. So we have compared with previous results. Here, the pristine graphene, no band gaps, our results and previous results by other authors. And you see a good agreement. If we compare with the first principles calculations, you also observe that the agreement is good. We have used Siesta, that program, in this case Siesta and Trans-Siesta. And you can also compute the local density of state. So that just to check in this case, for this configuration, that when the energy is at the Fermi level, so you don't have no transmission here. When your energy, the level is still lower than this band gap, of course here you don't have transmission, whereas when you go to higher levels of energy, you have different values here, different colors in color. The colors we have used, but you have transmission here. This is kind of another study that you can do in order to be sure that things are working fine. So, let's move to point defects. Point defects can be dislocation dipoles, dislocation quadrupoles. If they are very far away, one core dislocation core to another one, then you can conclude that they are point defects. So we have, as I said before, we have already studied the stability of the core structures that for different point defects. Now that what we have done, our recent work has been more on configurations of different combinations of point defects. So again, we use the same relaxation strategy. Periodic boundary conditions for the MVT relaxation, followed by this other relaxation with non-rigid periodic boundary conditions, flexible boundary conditions. In order, this step is just accounting, remember, for the out-of-plane displacements. Every time you have a 5-7 ring, you are going to have out-of-plane displacements. And you have to be careful, because the size of the cells are going to change. Otherwise, you are introducing some strain within the lattice, increasing the energy. So this is not giving you the right configuration. So if we start with dislocation dipoles, what do we observe? So we observe here if what we expect is to have this logarithmic evolution of the value of the energy, before and after relaxation, and if we compare with other results, this is the comparison. Again, here you have to be careful with the out-of-plane displacements, because you can end up with one of these metastable situations in which one core is both cores have a symmetric displacement out of plane displacements, let's say both up or both down. This is giving you a higher energy, whereas the real relaxed configuration is this one with lower energy, in which one of the cores is down and another one up. Again, you have to be careful plotted, otherwise you end up with differences on the relaxed configurations that you are going to start with when you want to study the electronic properties. Okay, so what happened with the quadrupoles? Well, here again, you have the out-of-plane displacements. In this case, you are going to have 4, 5, 7 rings. We introduce our defects this way. This is the lattice, the core of the dislocations before and after relaxation with the out-of-plane displacements. And if you plot the energies before relaxation, you are going to see that when this distance m is 5, this is the profile of the energy as a function of n, this other distance. Whereas for these values of m, you have these much higher energies. But this is just happening before relaxation. Once you relax the lattice, this is the energies that you are going to obtain. All of them the same. They don't depend on m, they only depend on the value of n. Within these values here, the energy is constant, independent on the side, meaning that the defects are point defects. They are isolated. They don't interact in between each other. Okay, but those are the numbers that you need to identify when they are isolated, when they are not. Those are the numbers that this procedure is providing. Okay, so the next study is, okay, let's work and see what arrays of dislocation dipoles do when they interact in between each other. So again, it's another situation in which geometry is important, because the geometry that you have is going to change completely the behavior that the lattice is going to, the electronic behavior of the lattice. So let's define a number of dipoles of a given length. This is the length of the dipoles, and this is the distance in between dipoles. Again, we are going to use n and m, although the value of m means distance in between different parallel dipoles. So remember, arrays of dislocation dipoles. So this is what we observe, the harmonic part, and this is what happens when you relax. When you relax the configuration, this is what happens in between this array of now of 5, 7 rings. You have a twin region. So this is the accommodation. Spontaneously you have twinning as an accommodation and relaxation mechanism. So it's going to depend on the length of the dipoles and the distance in between dipoles. Because when you have dipoles of the shortest ones, the Stonewell's dipoles, you don't observe any, there is no lamellar configuration in between these two boundaries, twin boundaries or walls, let's call it boundaries or walls. Whereas when you increase the the distance in between, the length of the dipoles, what you observe is here a misorientation, given misorientation angle that is going to change from this one to this one to this another one. So, and what happened? That we observe a significant reduction in energy. When we relax the configuration, this is the how the lattice relax, and the energy, you reduce the energy.
So yeah, so you call that twinning, but isn't twinning just some kind of reflection, like say a rectangular? You flip it around, and it's just that's my.
Let me. I will show you that the definition of twinning, that the mechanical definition of twinning, if you compute the angle and analytically and you compare with the angle that we obtained, they do agree. So it's a real twinning. When you apply the transformation to one lattice to another one, you already have twinning. So I will show it in a moment. So it's not a general rotation, it's a rotation that is a twinning. For that, you have to check that the equations that define twinning, these equations are already the ones that you can see here. The values of the misorientation angles are exactly the same, which is not what you observe. I mean, this is not grain boundaries. When I have defined grain boundaries, I have set up the grain A, grain B. I have rotated one with respect to the other one, and I have relaxed the configuration. And the 5-7 rings have appeared like with a different periodicity along the grain boundaries. This is a completely different thing. I start defining this. I introduce these slips within the lattice. These are the rings that we observe with the harmonic solution, and then when you fully relax the configuration, you observe this rotation. You have not introduced the rotation. It just shows up as an accommodation mechanism. So, yeah. What happens when we plot the misorientation angle for different configurations? So this is n changing, and the lines are different curves correspond to different separation in between dipoles. So we observe that for short dipoles, short meaning n less than 11, you have this behavior on the misorientation angle. Whereas for longer dipoles, this is the angle that you observe, constant. So it depends only on the value of m. This is the out-of-plane displacements that you observe, and local on the 5-7 rings, this for this configuration and this another one. Whereas when n is larger than 11, this is the kind of out-of-plane displacements that you observe. So you have the local wrinkles plus another wrinkles, structures that you observe within the lattice. When you plot the energy for these different configurations, this is what you observe. So again, for values larger than for long dipoles, this is the evolution that you observe in the energy, whereas this regime is completely different. You have a kind of transition regime in between short and long dipoles that correspond to this configuration. So it's kind of, they are not the same, because the out-of-plane displacements for the whole lattice is order of magnitude lower than the ones that you observe here. So this kind of a transition regime in between one and the other one. So let's compare, and because I have said twinning, and you don't really have to believe me, but in order for you to prove that this is twinning and not something different, I mean, you have to really see if the angles that we have obtained as an accommodation mechanism, let's repeat it again, are really twinning or not. So in order for this to be, this is the transformation that you are going to have in between this initial lattice and this another one. A and A plus has to be the same, and L plus has to be the same. So this is the deformation matrix that is describing twinning. And if you compute the angle from this analytical definition and compare with the computed ones, you see that they are in a very good agreement. So this is what we observe is twinning and not other kind of mechanism. So, but as I said, twinning is a kinematical mode of deformation. So it doesn't have to, it shouldn't depend on the interatomic potential that you are using in order to compute, to run your simulation. So for that, we have compared the results using IRIBU and this other Born order potential. And you see that the angle that we have observed is exactly the same, whereas the energies are not the same, because I mean, different interatomic potentials are going to have to use different lattice parameters, and so the differences in the energies are always going to be there. You cannot avoid them. But this angle is exactly the same using different interatomic potentials. Okay, we have also studied the thermal stability of these configurations that we have computed, obtained, the twin regions, and we see that they are stable up to this temperature. I mean, you know that we are not going to reach that temperature, so you can conclude that this is the defects that we observe are thermally stable. But it's interesting to see that at this temperature they start moving, the 5-7 defects at this temperature, whereas at this other temperature the kind of defects are far away from being the initial ones, and so you can say that this is not the defects that are not stable at this temperature. It's not important, this, I mean, the values of the temperature, but the temperatures that we observe here are lower, a bit 500 degrees lower, that the kind of same analogous behavior that you observe in a perfect lattice. So let's see the transport properties. So across twinning. Okay, so we compare here the curves that for the Stonewall's array, not twinning, with this other structure in which we have twinning, and you see that this configuration opens band gap again. We have computed different ones, and we observe that you see the gap that they opens are different. This is more or less the same order of magnitude that the ones opened by grain boundaries. But the mechanical mechanism is different. So different values for different lengths, different geometries, but you see here in this table, we have compared with first principles again to see if the values of the band gaps were in agreement with ones computed using the tie-binding model, and they are. And also we have compared the flat model with the model, the lattice with the out-of-plane displacements. Again, as we did observe for grain boundaries, we see that the band gaps are the same. So again, we can compute the local density of states. This is for the when we don't have twinning, the Stonewall's defects, the shortest one. And If you compute it for another configuration, you observe the same. For energy at the Fermi level, you don't have transmission. You don't have transmission here, not here. But as soon as you go to values of energy of the order of the band gap, you see transmission, and again here. Okay, so let me just, just 2 more slides, or 3. Let me talk a little bit about bilayers, what we have observed. So, point defects, isolated dislocation chords. What we have observed, we have defined 2 layers, a dipole in one of them and a dipole in the other one. And if they are both dipoles of this length are in registry, okay, so they move together out of plane, and the energy of the bilayer configuration is more or less the energy of one layer twice the value of one layer, meaning that there is no interactions in between them, and there is not the steric interactions in between the lattices. Whereas when you separate the dipoles, 15 angstroms in one layer and in the other one, in the upper layer and the lower layer, what you observe is that the energy of the bilayer is much higher. So there is a strong steric interactions between the layers, just because they are not much one defect against the other one. So you should study how the geometry, how the configuration that you define is going to give you different behaviors on the interactions. And if you study the whole regime, the whole separation in between the dipoles in upper and lower layer, what you observe is that for values lower than 13 angstroms, this is what you have. So no interactions. Whereas as soon as you increase this separation, you see these dramatically differences in the energy. And so this is what you have in this regime, and this is what you observe in the other regimes. So very strong interactions in between both layers. If you plot both configurations, and then you relax, you will see that you move from this stacking sequence, AA, to the AV. So still you are going to have these high energy interactions in between them, but the lattice is going to relax in such a way that this is the kind of stacking sequence that you're going to have, the one that you already expect to and has been observed at the ground state stacking sequence. With this, I would like to thank you for your attention.